All right, so the only thing that doesn't carry through or doesn't have a parallel is this, the sample size estimation when you're doing inference on the true mean with sigma unknown. So why can't we actually estimate the sample size? Okay, so you didn't get there yet. So where does this come from? Let's think back. Where did I get this number from? Can you answer that? Or this formula, sorry, from? I set this part to M. This is the margin of error. So let's do that. And then to solve, it'll look like I'll cross multiply. And then I'll square. So that's where this formula would come from. So it looks like the one above, but S instead of sigma. Okay, so what's wrong with that? Why don't I just do that? Okay, because you'll need S. And what is S? The problem is you'll need to get this from your sample, but that also depends on N. That's the problem. Okay, so you have another N inside here. You have not completely isolated for N. Now, so you could solve this with like with Excel, or you could make a program to solve for the N. All right, or you could get a program that solves for the N. And it would do it by iterating towards it. It would pick certain values of N and see if it balances the equation. And it'll try an approach with interpolation, or like in a different way, not in an analytical solve for N on one side way. Okay, so that's why we don't bother. So we do not bother with this because it's not really an isolation event. Do you follow? So returning to where we left off on page 46. Here. Okay, so we're coming full circle and we're going to talk about match pairs tests. And how we conduct them to test if we found that the results are different between the pair. So remembering how do we use matched pairs test? We take otherwise identical subjects, and we give one treatment and the other one a different treatment. One moment. And then we check to see if there's a difference between them. And now we know how to do kind of this difference testing by standardizing, right? To see if there's a significant difference found. So here's an example. I have, now this is a very small sample, just that we don't get hindered by the numbers. We want to test the significant effect of fertilizer treatment or the difference between two different fertilizer treatments. We can use a t-test after we've differenced given data. We will use a 5% level of significance for the test. We're going to look for an improvement. So we want to see if the fertilizer on one plot improves the yield of tomato plants more on, compared to using the old fertilizer. So here are the results on otherwise identical pairs. So this is called, matched pairs design or matched pairs test, and the results are from dependent samples. Okay, that's another abused word. I mean, it's overused word in statistics, but in this case, dependent samples. It means that the results come from the same sample, with the same kind of distribution. All right, so they're dependent samples, old and new. So here we have the yield on the first plant, and then on the matched plant in the same type of soil with otherwise the same conditions, has 2 pounds versus 2.2 pounds. And then this is the next pair, this is the next pair, and the fourth pair is here. So what we do with that is we collapse them into a difference set by taking the new one. Now you got to be careful about how you subtract them. That's about it, really. You subtract them and you make them one data set. You make them a single data set. Here. And so I'm going to take 2 minus 2.2, and I get the differenced values, and then I don't use this anymore. And I do that across the board, and I don't use this anymore, and these are gone. These are collapsed into one number. And this is my new data set. The difference data. I use a subscript D. You don't have to do that. It's just to make sure you realize that I did a step before I got here. So I have the difference data with an average of 0.175 and a standard deviation of 0.64. Now, how are you going to get these? Well, you put them in your calculator, right? Let's put them in our calculator. Go into second data, clear my worksheet, and I enter the numbers 0.2 negative, enter down, 0.5, enter down, 0.9, enter down, and 0.5 negative, enter down. And then I ask for second set. So now I open up the results. This is a linear, remember this? These are the linear results. I didn't put in 2 data sets, I just put in 1. So I get the mean of 175 and the standard deviation of 0.6397, but I round it to 3 decimal places. Using my original rule, right? 2 more decimal places than you started with. So that's how I get my results. And then I analyze the hypothesis test. Okay, so the question for you is, what am I testing? What is the hypothesis? Now you can read along in the notes, but think about it. What if there? So what the hypothesis, the null hypothesis is always that there's no effect or no difference from the status quo or no difference. So what would be the mean difference if there's no difference? In other words, if there was no difference between the old and the new, what should all these numbers be? So I'll say that again. If there's no difference, right, good. So there's no difference between old and new. When I subtract, I should have a 0 here. I should have a 0 here, approximately. So in fact, this number is kind of close to 0, right? I'm not sure because I don't really understand the distribution of the difference. I don't have prior information on how spread out or what the variation of these differences should be. I'm going to use the sample standard deviation for my measure of a dispersion or variation and see, is this close to 0 by checking it against 0. So the hypothesis will look like H0, HA. I'm going to put a mu and a mu equals. So what do I put in the box? What do I put in the box for people who still thinking about this? Whatever I put in the top, I have to put in the bottom. Yes. So we put a 0 here and a 0 here. And what sign am I going to use? How do I figure that out? Is it greater, less, or not equals? Right. So the effect, you think it's the same? Am I looking for the same? So you need to look back at the question. And what does it say? Determine the effect. You're right. It does say that. So if I want to look for an improvement, I would say to see if the second one is greater than the previous one, right? If I want to look for a reduction, or a worsening, you would use that one. If there's no effect, you would use not equals. In this case, even though I just said the effect, I want to look for an improvement. So it's going to be right tail. That's what's going to go there. Okay, so think about that. So it improved, it didn't get reduced, and it was not no effect. I'm interested in it being better. So I have a new fertilizer I'm going to test. Is the new fertilizer better than the old fertilizer? So that's all I have to say here. And I call it the one sample T procedure. It's like a matched pairs or dependent tests. Those are all the same thing. Okay, so I just summarized down here the different things you would do. All right, so this is my test. And when I started doing T distribution, I said to you, I'm going to just do assume and assess in one step and just calculate the T stat. So this is the test statistic. This is a statistic. I'm taking the results of the sample and testing. Okay, so when I standardize this, is this too many standard deviations away? So it's half of one standard deviation away from 0. We have no idea what that means, right? Because we're not familiar with the T distribution. We don't know, is that an outlier? We don't know. So what we do is we check. So we learned everything we learned in very familiar territory with the normal distribution, but now we can do this with different distributions. So this is going to be my T degrees of freedom. Because there were 4, degrees of freedom is 3. So I'm going to use the T3 and I am going to draw where my T stat is. I'm not sure if you guys have like super rain, but I have a lot of rain right now. I'm looking out the window, so I got distracted. Is it very rainy where you are? Okay, so let's draw onto here. So 0 is always in the middle. It's just like the Z. However, depending on the sample size, your distribution will be more flat with larger tails or more peaked. In this case, it's going to be flat with larger tails. And so I'm going to draw 0.547. And I'm going to test to see this way, right? Because I always look in the direction I look in the direction of my alternative hypothesis. And so I'll just ask you again, looking at that, does that look like it's an outlier? Is it far in the tail? Is it unusual? Again, we really don't know. We're not that familiar with this distribution, but it doesn't look like it the way I've drawn it. So let's get the p-value, because that's going to make it all clear for us, right? Because the p-value is a standardized way of looking at things. Even though I have the standard deviations from the mean, I don't know what that means. So that's why I get a p-value when the distribution is not familiar. I'm not familiar with it. So let's do that. So all I've done these steps. Let's get the p-value. P-value is equal to is my p-value. The chance of being as extreme or more extreme. So I draw my test statistic. Let me put that in. I use the direction given here, and then I calculate the p-value. So let's go. You can put it in Excel. You have to do 1- approach though, because the Excel just gives you the left side. But let's go to the T distribution. Let's see. So here's a distribution. We need to be at the 3rd one. Let's clean this up a bit. Okay, so I'll take this with me from here. Oh my goodness, I hit the wrong thing. And I hit the wrong thing. 1 minute. Oh, I was actually over here. Okay, so we are in the third row. I'll make it bigger. Oh no, I didn't want to do that. Let's make it big. So we're in the third row and we're looking for this number 0.547, which is, it's not even on the chart. So what does it mean? So what's on the chart are the numbers beyond that. So starting over here. Right? So what does it mean? What does it mean if this is beyond this one over here? So let's put this on the chart, 0.765 onto my graph. So how do we, using this, how do we summarize?
Cannot reject the null hypothesis.
No, I'm not, I don't mean that. I don't want to jump there. I want the p-value. So what's the p-value? Before we go there, certainly we will reject. You're right.
The p-value is going to be larger than 0.25.
Okay, what is the limit? It's larger, but it's smaller than what? You bound it. It can't be more than 50, right? Because it's a positive number. So this will bound it. It's between 25 and 50%. The point is, it's not unusual. It's very likely. If the null hypothesis is true, if we assume that, then the result we got is normal. It's very expected. It's 25 to 50% possible to see that result. So what we're doing then is, I'm going to do all the steps here, then we'll look at the graph. So this is step 2 and 3. This is step 4. And then step 5, see, I could squeeze it all in here. So I write so as I explained, this is your standard to remember. The conclusion is always the same conclusion, no matter the direction, doesn't have to do with the alternative. It's a test to see if what you got is unusual. So your p-value was between 25 to 50%. That is less than 5%. That is not, sorry, less than 5%. So we say we failed to reject. We didn't find anything unusual. Our assumption stands. So the test is not significant. In other words, in words, there was no improvement. The new fertilizer did not improve yield. So I've drawn things here. This is our result. Clearly, it falls in the fail to reject H0 region, right? So this is all failed to reject. Rejecting would require more than, for this distribution with 3 degrees of freedom, it has to be more than 2.353 standard deviations higher. Okay, so that's more than, well, that's similar to the Z, because for 5% on the Z, you would be at, I'd have to check. 5% on the Z, let me just see. So 5% on Z would put us yeah, 1.645 between these two. So just to make a note about that. If you were doing a Z test, this would have been so this is much further out, right? To get 5%. In the tail. Anyway, so my conclusion is that it's not unusual, so I failed to reject. I sort of repeat myself many times. So you appreciate more why we have to do a p-value now that we use a different distribution that we're not so familiar with. Trying to say here, if you're using the C distribution, okay. So then I just have a bunch of different exercises, a number of exercises you can practice. And I have the results, and I hope my printing, all my graphs show up. Sometimes they get distorted. Let me know. Let's see, let's look at some of the Okay, so let's look at some of the results, the output. Okay, so we don't know anything about this problem. We just have some output. I won't read the problem. Let's just look at the output and see, is the test significant? Can we just derive that from just staring at the output? I'll give you a second to look at that and then I'll answer my own question. So let's see what we have here. Which mean is this? What are moments? Yeah. What did you say? Oh, okay, in words, yeah, without reading the problem, I'm just gonna look at the output, get comfortable with just reading output. And answer the question, is the test significant? I know we'll read the problem after, but so here, this is these are the results, these are the statistics, right, of the sample. So these are the findings in the sample. This is the sample statistics. Or I guess that's redundant. So these are the statistics. So this is X bar. This is, so what is this? The second one? So 305 is X bar. Those are the moments, the results of the sample. What's 4.08248829? Yeah, very good. So that's the sample standard deviation. What is the sample standard error of the mean? This is what? 2.04. How do you get that number? Not M. It's not the margin of error, the standard error. So it's the standard deviation of X bar sigma not known. So let's go back to the formula sheet. So this is the standard error if sigma is known, and this, or standard deviation, right? Sigma is known. And this is the standard error, S over N. We did it last class, S over N, or square root of N. So that's the standard error. So this is S divided by square root N. N is here. And what is this? How do you get this number? 311. Or what is that upper 95% mean? No idea. You guys are busy thinking. This is X bar plus 1.96 times S over root N. It's the upper limit of the confidence interval. So really call these are the statistics, right? From the sample. And this one is X bar minus 1.96 F S over root N. You can verify, check them. That's all it is. They did it all for you. So now all you have to do is interpret. Interpret what? So the test is the test for mean. So I'm going to use mu equals. So what goes in the box? What are we going to hypothesize the true mean is without any prior information? Or what does the status quo mean?
Would be the 300.
So you get that from here, right? So it tells you right here, you're gonna hypothesize that it's 300. Whatever you put here, you also put here. And what are we gonna test? What test are we conducting according to this output?
If it's higher.
Right, so the bolded thing is telling us that we're looking at it's higher. So we got all that from this output. So now let's conduct the test. I mean, the results are here, but let's do it on the side here. So H, so what's the next? Assume and assess. So the T stat is X bar minus mu0 divided by, which is this, S over root N. So we have all these numbers. X bar is 305, mu is 300, S over root N over here is 2.04. So I can get all the values there. So X bar is 305 minus hypothesize 300. So it's 5. The sample was 5 higher than the hypothesized. So it's a matter of standardizing to see if we're far away in statistical terms. So then divide by 2.04. We'll take just like that, 2.04. And then when you do that, you get how many standard errors away?
2.45.
Exactly. So the number is right here. Okay, so that's your T-stat. It's right there. Hope I'm making this simple and not making you think there's something new here. So this is 2.45. And then the p-value is given as you draw the T-stat on the curve, that is T3, and it's equal to 2.45, and you test on the right side, and it's given to you already. The p-value is given as 0.0459. So how do we conclude? So everything is here. You could actually just conclude right off this page. So you conclude always remembering to test p-value, the tail, the chance of seeing that T-stat or more extreme, in this case, higher is 4.59%. So the 0.0459 is less than 0.05, or you could write it 4.59 is less than 5%. So you do reject the null hypothesis, and the test is significant. Statistically significant. And so now we go back and see what in the world are we talking about? So what in words of this problem, so let's read the problem. So we could do that without even knowing the problem, okay? It's all there. I mean, I did bold this to show you which test we wanted because the output would just give you all the results. This is a SaaS software that did this. You could figure it out in Excel. I'm not going to show you in Excel, but if you want, you can figure out how to do it in Excel and how to interpret, but you should get output similar to this. So let's read the problem. My goal is to help you able to do this with a simple calculator and some contemplation. You don't need a expensive software to do stats. I mean, well, not interpreting stats. To conduct statistics and complex statistics, yeah, okay. But yes, you can do quite a bit with very simple tools. More efficiently with those tools, with statistical tools, but you're learning, so I prefer you do things manually. I talked to my undergraduate students and they teach statistics at the undergraduate level with R Studio. It's a free statistical software. So yeah, okay, so statistics software doesn't have to be expensive. You can use R, but ask them if they learned anything. I mean, the students don't know statistics. Now, that might just be because of their age or lack of interest, or they're not intending to be statisticians, but it's a shame because they have at least 6 credits in statistics and they didn't learn anything. So I prefer to use this method of problem solving manually. And then, you know, it's easy to read output when it comes to the time you have to, if you know what you're doing. So you don't have to learn how to get the output. That's easy enough too, if most kids are tech savvy. All right, so a manufacturer of ovens is concerned that the dial indicating the oven temperature for a certain model oven is overestimating its temperature. 4 ovens of this model are selected at random. The dial on each is set to 300 degrees. Okay, so and after 1 hour, the actual temperature is measured. Okay, so these are the results, 4 results from a sample. And they're around 300, only one is exactly 300. So let's test if it's overestimating the temperature. So we're testing the calibration of the dial. And we did all these steps. So in the end, we rejected the hypothesis that they were set at 300. And in fact, yes, they are overestimating the temperature. So there is sufficient evidence to suggest the temperature is overestimated. Okay, good. So I have problems and problems and problems for you here. And then, okay, so you can stop studying here for the test, but I want to say a few things. I put some other stuff in here because it can just be overwhelming, but you really should know that you can do other kinds of tests. Okay, so the same sort of technique where you're setting up a hypothesis and testing it by getting a test statistic, p-value, and all of that. The only thing that's going to change from test to test to test is calculation of the standard error. Okay, so here's a test of 2 independent samples. Now, I'm not going to require this, like I said, for the exam, but you should be able to jump to this kind of you should be able to read output similarly for different kinds of significance testing. So did the proportion of undergraduate students, cell phone users, owners increase significantly by 3% over the years 2003 to 2004? Or are these differences merely what we would expect to see due to random variation? The following data was obtained from a 2005 press release from the Student Monitor. In 2003, 83% of students said they had a cell phone. In 2004, 89% had cell phones. So is this an increase? It looks like an increase, but that's all the information we have. Given that the sample size of each simple random sample has 1,200 students in 2003 and 1,100 in 2004, compare these 2 years with a significance test. Carefully word your conclusion. So we're looking at the difference between the proportions is no more than, it's not more or less than 3%. So this is how you set up the test. Proportion 1, proportion 2. And then you have to use the same rule. And we're going to use Z, right? Because it's a proportion test. We use a Z test, using the standard normal table. We need a point estimate, a hypothesized value, and the standard error. The only thing that is maybe new is getting the standard error. So this is the standard error you're going to use for independent samples. So remember, for dependent samples, we just subtracted the pairs, but this is what we have to do for independent samples. So it's just a different standard error calculation. That looks like, anyway, it looks familiar, right? Because this is the, this is like the variance. This is the variance of the first populations. This is like an estimate of the variance of the first proportion or population proportion. And then this is the standard error of the variance of the second populations. So all this stuff looks familiar, but it's a little bit different. And then you also get a p-value once you get the result. So this is going to be, this works out to being negative 2.09. And then it's because it's a not equals to test, you go back, it reduces back to the standard normal table, and you do the two-sided test and you get this result. And again, this is less than 5%, so you reject. So you find that they it did go up. So 3% compared to sorry, what was it? It was a 3% difference. So it was 83 to 89, and we want to check if that's more than 3% increase. And it is, right? Because just looking at it, it's 5%. And so we're checking, or 6%, sorry, the 6% difference, and we're checking to see if that's greater than 3 for whatever reason. Just so it's just an example. And we do find that it's more than 3% increase in usage. So the point is, you can reduce everything to a z-stat, and no matter what problem it is, you can see if the test is significant from those results. All right, so the assumption here, note that I used the estimate of the true proportion to calculate the standard errors. What about two samples looking at means being the same, not proportions? So here I have an example of that. And again, I'm not going to test you on this. I'm just showing you that it's the same sort of process. The only thing that's ever going to change is the standard error. Now noticing this looks very familiar. So this is for a test of means, difference of the means. And again, it's not pair, they're independent samples, and we assume unknown sigmas, right? So with unknown sigmas, we have to use S, and we have a similar thing where we're taking the variance and adding them and square rooting them. This comes from the rules of means and variances, right? To combine them, and assuming they're independent, I don't have to have that covariance term. So this is like, it's a combined sample, it's a combined variable or joint distribution. So if you remember back about the variance of a new random variable, remember x1 plus x2. If you remember back to the rules of means and variance, if the variables are independent, then this is just going to be if you remember back, I'm just trying to clue you in there. So that's, if they're independent variables, then that's what you get, right? Oh, I'm going to put not x1, I'll just put 1. Let me put x and y, maybe it'll better ring a bell. Shouldn't matter, but okay, so that's why all we're doing is adding, and then we take the square root because we work with the standard error, right? Or standard deviation. So this is similar, blah, blah, blah. And then the only other catch is this degrees of freedom calculation. So this is why, you end up using software beyond this point, because you're going to really calculate all this stuff. You can, at this point, learn how to get these results out of software and how to interpret your results. Okay. Look at the p-value, less than 5%, it means your test is significant. And then I talk a little bit more about some other stuff. So this is just the conclusion here of how to do a test for two means for independent samples where sigma 1, sigma 2 are known, but assumed to be equal. This is your result. If they're different, you do this result. All right, so these are the considerations that you need to make. All right, the last thing, something like this. Now, this is very, very common type of test, and it's funny because it's like nobody remembers this, but this is very, very common, and you'll do this kind of a test, a chi-square test of independence for the type of data, survey data that we learned about in the first module for designing experiments and sample surveys. So to analyze categorical variables, this is the simplest thing I'm going to show you. And I really like this test. You end up using this a lot. To analyze the relationship between two categorical variables with two levels, we can use the chi-square test. The null hypothesis of interest in a two-way table is there is no association. So again, null hypothesis is no difference or nothing happening, right? Nothing surprising, nothing new. There is no association between the row variable and the column variable. The alternative hypothesis is that there is an association between the two variables. So the alternative HA does not specify any particular direction for the association. So we cannot describe HA as one-sided or two-sided. This makes it even easier. So let's say we want to see, is there a relationship between gender and binge drinking? So in other words, are men more likely, or do men have a greater preponderance or less? We don't want just a different preponderance than women to be binge drinkers. So here are my results. In this sample, I have 1,392 men said yes, they're binge drinkers, and 1,748 said women said they are binge drinkers. This many men said no, they're not, and this many women said no, they're not. So it's really important these numbers are relative to how many were interviewed. Now, it's common that women are more likely to answer a survey. You see that right here. So this number being larger than this number means nothing. You have to relate it back to the total, right? So this whole thing about comparing proportions depends on what to expect. So you're going to make the null hypothesis that there is no difference. So the same proportions should be in each cell. In other words, should be all the same proportions in each cell. So we're going to test that. And the way we test that is calculating what's called a chi-square statistic. So you take the observed number, you minus by what's expected. And what's expected is, again, the same proportion in each one. Do I do that here? So this are the expected counts here. Just looking if I have the formula for the expected. Oh, it's right here. Okay, so the expected count is the row total times the column total divided by the total number of people sampled. And so you have your expected column. So this is like a long thing that you can calculate the chi-square with, but you can get these numbers. Again, this comes out of Excel very neatly. So you get these expected numbers, and then you calculate the difference between the observed expected square divided by the expected count, and you sum them all up. This is your degrees of freedom. And so this looks very different, but it's actually very neat and easy. And you end up with a chi-squared statistic. That's how you say that. It's a chi-square. And then you test it. And a chi-square distribution changes no matter depending on the sample size. And it becomes flatter and wider. Otherwise, it's very peaked as the sample size goes up. It's longer distribution. So it turns out that the p-value for the chi-square test is 0, which in this case, it's smaller than 5%. So we reject. What are we rejecting? So that's the main thing I want to get to. What are we rejecting? We're rejecting the null. The null was there's no association. So it means that there is a difference. And from the results, we see that men tend to be more likely to be binge drinkers, and the result is significant. So the main thing to get out of here is not to do all the steps and calculations, to be able to interpret what you have. What you really need to know about tests, if you're going to use software, is what is the null hypothesis? The null hypothesis is no association. So if you reject it, then there is an association. And then looking at your results, you say, so men, you know, although less were interviewed, they are, you know, so then you just do this calculation because I don't have that number anywhere. So 1392 divided by 5348. What is that? I can put that here. One, 392 divided by 5348. So 26%. And 1748 divided by 8471. So men was higher, right? Men was 20. So women are 21%, men are 26. So just you see that there's a difference statistically, and then you just look and say, it looks like men are higher, but you'd have to. So this is where I want to go. Is it 21? Yeah, it's 21. So if you have a test, that's significantly different result. And so here's my question. My question is, I don't have even the test written up here. I have also the chi-square test there. You guys can read it. Again, it's not on the exam. It's just to show you that you have the knowledge to do all sorts of statistics now, if you followed and gotten the basics down. Okay, so my question is, let's see. Okay, so let's say you found out that you have you do a two-sided test and you find the test is significant. Can you conclude that the result demonstrates a higher or lower Trying to make this as general as possible. So if you find a two-sided test is significant, can you then conclude that the result demonstrates that the parameter is higher or lower than hypothesized? So that's my question. So what I'm getting at is, if you found a two-sided test is significant, whether it's Z or T, you fall in this region. Now, remembering that this and this are the p-value, right? Not p-value, the alpha. So if you've rejected, it means that your test statistic is over here somewhere. It's either in here, in this blue area, or this blue area. So let's say it's here. Without conducting the right-sided test, what do I know? I don't have to, do I automatically have the results of the right-sided test? This is evidence that the parameter is higher than hypothesized, because if I do the one-sided test, it's going to put me, it's just going to be on the one side, and it's going to have 5% on the right side. So this will still fall on the 5%. So it gives you the result for the two-sided test and automatically the result for the one-sided test. Okay, so if you do the two-sided test, so that's why you often see people will just do, or if you read research, they'll just do the test of difference. And then that will satisfy to say it's higher or lower. Okay, so my question was, if you find a two-sided test is significant, can you conclude the result demonstrates that the parameter is higher or lower than hypothesized? So if it's like that, that's evidence. So what if it was the other way? And draw it here. So this is my my alpha, my rejection area, usually 5%. And if it turns out my test statistic is here, and that's why I'm rejecting, then this is evidence of what? Okay, so doing the two-sided test and getting a significant result automatically gives you your results for the one-sided test. However, if you do a two-sided test and don't get a significant result, you still have to do the one-sided test. Should I write that down? Doing a two-sided test automatically gives you your one-sided results. But doing the two-sided and failing to reject, you still have to do the one-sided results. Okay, let's see if I can put it all on the same page. So you don't have to do the one-sided test. If your test statistic was here, you say it's higher. If the test statistic was here, you say it's lower. Okay. So if it's not significant, it's out here, you don't bound it, you don't know where it is, right? So it's out here or here, you don't know, you'd have to check to see if it's still, if it's on this side, you do the right-sided test. If it's on this side, you do the left-sided test to see if it's higher or lower. Let me just write it like that. If you're really trying to get an answer, did it change? Is it higher or lower? This would be the procedure, right? So you do a two-sided test. And once you've done the two-sided test, you already have the result that it was higher or lower. But if the two-sided test is not significant, depending if your test statistic is negative or positive. So I'm just trying to show you how you do this in practice, because no one's going to tell you, do a left test, do a right test, like I'm doing here. I'm just teaching you, we're just practicing doing both tests, but this is how you do it in practice. And that's why you'll see most tests are that they're not the same, because that will give you your result all at once. Hope you can read that. So having a non-significant two-sided test, conduct a one-sided test on the left if a negative test statistic, and on the right if a positive test statistic. Questions? Okay, what I want to do next is go to the homework questions. I'll let you write that. Let's take 5 minutes. Let's come back at 10:40. Sorry, I took a longer break. I should have just said 10:45. Okay, so let's go into the homework. The homework exercises. Who has started the homework? Anyone? Or who's working with the homework? Who has started doing the homework? How's it going, Marcos? It's okay. Mhm. Okay, so this is why I want to go into the homework. Exactly what Marcos is raising, that when do you use which formula? All right. So I put that there. Exactly what I knew you needed help with. Okay, so what we're going to do is we're going to read a few problems. And that's all we're going to do. We're going to read the problems and decide which formula we're going to apply. And in terms of doing them, you guys can do them after. You do have the solutions to all the homework exercises, but try not to look until you've attempted them, or you just won't appreciate what you've learned. All right, so let's look at the first one. A gas utility company wishes to know how much time is needed for the service person to handle a service call. A random sample of 16. So let's not waste any time. Let's start identifying what we have. So this is a sample. Sorry, let me do that again. A random sample of 16 gave an average time of 62.2. So why I'm doing this is, let's just do this and then I'll explain why I'm doing this way. This is what is this? Which mean, Patricia? Which mean? That's the whole point. Which mean? Sample or population? Sample or population? Sample, mean, X bar. Really important. Okay, and then with the standard deviation of 5, what is this? What is this? Aha, Marcos. Marcos says it's S. Any other thoughts? Anyone else? Okay, Patricia says it might be sigma. So is it sigma, the sample standard deviation, or is it, what did I say? Is it S, the sample standard deviation, or is it sigma, the population standard deviation? Okay, you think it's sigma. Okay, let's read the sentence again. A random sample of 16 gave an average time of 62.2 and a standard deviation of 5. So the keyword here is over here, sample. This is sample result. Very good. Okay, so you guys see it is confusing, but you have to read the sentence from the top. So this is S, and it is confusing. This is why we're doing this, okay? Do I have any other information? All I have is a sample. When all I have is a sample, I go here. Number 6. Okay. Okay. So when all I have is a sample, I have to use number 6, the T. So I'm going to calculate, it's asking for the 95% confidence level. So you do X bar plus or minus. Z star is 1.96. Not D star. I'm going to put the formula down because I just messed it up. So T star and then S over root N. That's the confidence interval. X bar we have, S we have, and we have, and T star for 95%. How am I going to find it? What am I missing? Degrees of freedom is from here, degree of freedom is 15. So find that value for me and I will leave it the rest to you. So find me the T 95% with 15 degrees of freedom. Anybody? You looking? You waiting for me? I'm waiting for you. So for 95% going from the bottom up to 15, it's this one. T point, yes. T equals 2.132, Marcos. 2.132. Marla, are you good? 2 point. So from the bottom, go from the bottom, just to avoid confusion, because it can be confusing. 2.132. Also, you can use Excel. What would you put in Excel? So in Excel, to get that number, you remember where it comes from. For 95%, this is 2.5%. So you're gonna pick the T distribution, the left side of 2.5%, 0.025. And that should give you the value as well. Okay, let's do the next one. No, let's do number 3. We draw a sample of size 9 from a normal distribution with a mean of mu equals 75 and S squared, so it's pretty clear, equals 48. So the confidence interval for mu is I don't think this is supposed to be mean mu. This should be mean X bar, no? Very bad. That's a typo. Never noticed before. This should be X bar. So that can be confusing. All right, so this is the sample result. We draw a sample and compute X bar is 75 and S squared is 48. So you need to use not S squared, but S for the formula. So the square root of 48. I'm just going to put S squared is 48. And so what you need is X bar plus or minus T star S over root N. So S over root N is 48 square root divided by N square root, which is 3. I'll just put square root 9. It might look confusing if I do that though, but. So remember, because they give you S squared, it's 48 divided by 3. And that should give you, well, let's see, what does it give you? I'll write it in here. Just one moment, I have to check something. Okay, so 48 divided by 9 square root. So this is what's going on here. I know. What's going on in this one? It's so funny. This one's a messed up problem. Because when I made this, I took it from a PDF that I had. And some of the symbols and some of the numbers got messed up. So maybe that's my excuse. So what's going on here? So S over square root of N. .31. Okay. I did it. Yeah. So T star. So this is the tricky part. Yes, T star for 95% and Degrees of freedom are 8. So we got to go back to the table from the bottom. 95, if you can see. And degrees of freedom are 8. It's 2.306 over here. So you don't have to actually calculate the upper and lower limits. I'm just giving you the options, and the best answer is D. All right, so I actually had a typo here. I'm gonna go and try and fix this. I should put that. I never noticed that one. I usually skip that question probably when I illustrate. So that's confusing on the first page of your notes. Okay, so but usually when you read this, it doesn't screw that up. Okay, so it usually says sample results, and then anything else would be population results. Let's try number 4. So we'll do a few more and then we'll just go unless you have questions for me. We'll go early. So a cannery prints 16 ounces on the label of one of its products. The quality control supervisor selects 9 cans at random and weighs them. He finds that the average weight of 9 cans is 15.7 ounces and standard deviation of 9 cans is 0.5. An 80% confidence interval, blah, blah, blah. Okay, so cannery prints 16 ounces on the label. The quality control, 9 cans at random. Okay, so that's 9 is N. So degrees of freedom is 8. Average weight of 9. So this is the sample, right? So X bar is 9. Sorry, not 9. X bar of 9 cans is 15.7 ounces and standard deviation of 0.5. All we need then is a T star for 80% confidence interval with a degrees of freedom 8. There's no other information here. So we go back up. Now we're going to go up the 80% if it's there. So here it is, 80%. And we go up to 8. It's 1.397. 1.397. If it wasn't on the table, you would go into an Excel, and which would you look, what would you do in Excel? In Excel, you would look, oops, terrible drawing. So for 80% in the middle, you need 10% this way for a T8. And you want to find T star negative. So that's what you would get in Excel. That's what you would look up in Excel. 10% on the left. Do you want me to do it? Okay, so let's see Excel. So if we didn't have it on the table, we would go onto Excel. So you're gonna do T distribution. You want the regular T distribution. You want just the one side for X of, no, I don't want this way, do I? I want the inverse problem. So I need the inverse T distribution. So T, oh, that looks terrible. So let's do this here. T, T, I want the inverse. And I put the, no, I'm doing this. Why am I confused? I'm just so confused today about this. T, do this one more time. T, distribution. I have to put the X, I have to put the probability. I know it's the inverse, right? I'm so confused. Why am I confused? Inverse, the probability I want to put is 10%. Now, do I put it as a decimal? Let's do that. And then the degrees of freedom is 8. So that's the way to do it because I'm doing the inverse problem. There it is, negative 1.397. And the formula is screw that. So put the decimal value in there using the inverse because you're going backwards. Oh. Okay. Okay. So the best answer is, we need to calculate S over root n first. 0.5. The square root of n is 3. So which is the best answer? Uh-oh, what did I do? I transcribed my number wrong. 0.1.
Yeah, 0.1. Yeah.
Sorry,
167.
this is 0.1. So which is the best answer? See. Okay, let's do a few more. Let's just pick them. Pick some sample size estimation and some hypothesis testing, right? So this This set of exercises is focusing on the last material you learned, the T distribution that's being applied for estimations of mu with sigma unknown, because that's the most realistic. Okay, so we leave off on a high point, giving you something very practical. Oops. Okay, so let's see. How about let's try 7. The blood pressure of adult males is normally distributed with a mean, with a standard deviation of sigma. So what is 5? What is 5? Is it a sample result or a population result? Is it so Markel thinks it's a sample. Anybody differ? That it's a sample result, or is it a population result?
I believe it's population because it's not specifying that it's a sample.
Okay, so it needs to say these are the sample results, right? So here it says the blood pressure of an adult male is normally distributed with standard deviation 5. So that is the population result. So this is sigma. In order to estimate the mean blood pressure to within 2.5, so what is 2.5? Within 2.5 units, confidence level 99%. Okay, Marla says that 2.5 is X bar. What do you think? Edgar says it's the error. What is the margin of error? Very good. So that's actually M. It's actually the other side of the, not the X bar, it's M 2.5. And then, so let's look back here. So what we're doing is we're using number 5 now because we have sigma, which is better when we have sigma because these are exact, you know, this is great. We have sigma, we can use Z, and we're using this formula here. So we need Z star, sigma, and M. We have M, we have sigma, we just have to get Z star, and don't forget to square. So N equals C star, the zoom formula, master formula. So Z star for 99%, we can get that from our T table. Remember at the very bottom, we know, you know, the other value. So let's go to the T table. For 99%, sorry. So it's right here, 2.576. Right, 2.576. Oh, why did I do that? 2.576. Okay, so we put 2.576. Sigma is 5. M is 2.5. And what's the answer? The 26.54 is rounded all the way up to 27. So that's the best answer. Okay. Try 8. Who's Nostrum? And who is Nostrum? And because I don't have the name for my asistencia. I could do it by process of elimination, but I want to be sure. No comments. Oh. Okay, let's see. Okay, it is assumed that the heights in inches of men are distributed normal with a variance of 6.25. So this is sigma 6.25. So sigma squared. So sigma is the square root of that. because that is the population result, but it's the variance. So 6.25 square root is 2.5. So you have the sigma. The unknown mean is mu estimated within 0.5. So this is your M. And then the probability with a probability of 0.95%. So this is telling you you want the Z star of 1.96 because we have memorized that that's for 95% confidence interval, right? So putting all this together in a formula, Z star is 1.96. Sigma is 2.5. Don't forget to square. And M is 0.5. Always make sure you pay attention to your units as well. We are looking at the sample size. So N is, so we can do this because sigma was known, right? If sigma was unknown, we could not do this. So this is not correct. We can only not do, that's not the answer. So there we have to calculate 1.96 times 2.5 divided by 0.5 squared is 96.04, which we round up to 97. Okay. Questions? Okay. So you guys can do most of these. Let's get into hypothesis testing. Let's look at 14. So for 14, do you use the formulas of 5 or the formulas of 6 on the formula sheet? Minus is 6. Anybody else? All samples. So for 6, okay, so let's go and see what we have. Let's read. By law, the manufacturer of a food product is required to list the contents of the product on the package. Suppose a researcher for the magazine Canadian Consumer wishes to estimate the mean sugar content in a 16-ounce box of cornflakes. The standard deviation of sugar content in the box of last year's cornflakes was sigma 0.2 ounces.
It's also saying that the distribution is normal.
It's more about the fact that you have sigma, yeah, and that it's normal.
Yeah.
But it's more about having sigma and the sigma being relevant.
Yeah.
Because as long as it's large enough, you can still use this result. The sample size is the sample size is 5. It's not, so you have to assume a normal distribution. It doesn't say anything here. You would have to assume a normal distribution.
No, it says, and the distribution of the sugar content is normal.
Oh. And the distribution, why can't I see that? Yeah, it's here.
Yeah.
It would have to say that. If it doesn't say it, you just assume it. Otherwise, you can't do this problem. Because the sample size is 5. And so keeping to continue to read, you get a sample here. So from here, you calculate X bar. How do we get X bar? We use our calculators. And we put it into data mode. We clear the worksheet and we enter 3.2, enter down, down. 3.1, enter down, down. 3.5, enter down, down. 2.9, enter down, down. 3.3, enter. And then second stat, and you scroll through and you get the mean of 3.2. You also get S, but you don't need S because you have sigma. Sigma is always better than S. So 3.2. So they're all 3.2, so you don't even have to calculate that because there's no option. Unless you want to find an error in my lava here or my question. So X bar is that, and then we just use the formula X bar plus or minus C star sigma over root N. And you have all the values, so you guys can do that one. Okay, I'll leave that to you. So I just want to do setup. Let's say we were doing the hypothesis test here. What would be the hypothesis? What would be in the box? .2 ounces of cornflakes? No, wait, the mean.
3.2.
Nope. she wishes to estimate the mean content in a 16-ounce box of cornflakes. By law, they have to list the standard deviation. She actually, oh no, we don't have the information here. So we can't, this is not a hypothesis test because we weren't given the status quo. So we wouldn't do a hypothesis test here. So let's say you were asked to test if true mean is 3. What would you do?
Yeah, then it would be 3.
And you put 3 here. And then, and then what would be the sign?
Not equal to 3.
Right, so if you want to test if it is or it is not, so you put not equals 3. Now, in this case, tell me what's the result? If you remember, I taught you last week that for a two-sided test, all you have to do is make the confidence interval and check if 3 is inside. If 3 is inside, then you have no evidence against 3 being the true mean. So find the right answer and then check if 3 is inside. So I give you an extra problem to do there. So in general, if given sigma, you don't need S, right? You don't use, the best case is to use the true standard deviation. Okay, so which one is it? A through D. A through E. Which one is the answer? So right off the bat, you know it's A or C because it's 1.96. So it's either this one or this one. And so you just need to get sigma over root n. All you have to calculate is 0.2 over square root of 5. All you have to do. The answer is A. All right, so now is 3 in that interval? So you have to expand the interval. So I'll just show you how I would do that quickly with the calculator. Thank you, Marcos. So with the calculator, I would take 1.96 times 0.089, and then I would store that in the first one. Oh, what happened? Do that again. 1.96 times 0.089. Store it in my memory, store 1, and then take 3.2 minus, recall 1 is 3.02, and then 3.2 plus recall 1. So that's 3.374. Is that what you got, Marcos? Yes. So, I mean, I got this number because I used exactly these values here, but it's fine if you have a little bit off for not rounding, which is better actually. So the point is 3 is not here. 3 is before. So that means that you would reject the null here. And the test would be significantly different from 3. It's a little bit higher. You have evidence that mu is greater than 3. Right? Like I said before, if you do the two-sided test, you can say something about it being higher or lower depending on your results. Okay, so let's continue. We have still some time. Are you guys good? You guys getting the hang of this? So we didn't have to do all this. I just added this question on, thought it would be. But so you do this only for a two-sided test. Can you do the confidence interval? It just was guiding me in that direction, you know, the way it was worded. So I decided to put in a hypothesis. Let me just jump ahead. So you should do all these. I know there's 90 problems, but it's worth it. You have time. I mean, according to our schedule, you have time, maybe not according to yours. Okay, let's look at 23. So this will be the last one I do. This will be the last one I do, and then I'll leave it to you to work with next week. For next week, I'm going to put up an assignment, and you should do which is optional if you're happy with your grades so far, but you can do it if you're not so happy and you want to have you want to replace one of the assignment scores. And also work on the mock final exam if you haven't already. The answers are there, but do not look at the answers or solutions. So sit alone for 3 hours and try it, okay? Only your formula sheet. So to only take your formula sheet with you. Calculator. Yeah, put it on Connect. And you also have all those practice assignments to look at. If you haven't already, try those as well. Okay, so let's see. Well, the other thing to mention, if you didn't already, you should be able to see the look at the approximate exam distribution to get an idea of what's on the test. If you haven't looked at that already, that's posted in module 9 as well. All right, let's see what we have here. Horticulturalist wishes to estimate MECU, the mean growth of seedlings in a large.
Professor, excuse me, when are you uploading the final? And we had discussed, maybe wanted to see if we can meet after the final to review it.
Well, the final will be up on the 8th. I'm not changing that.
Okay.
And then it's up for, I said 72 hours, and I think I have time. I checked to see if I have time, but you're saying before I post the grades, you want to see you want to review the final?
Yeah, if we can do something similar like we did with the midterm.
Usually I don't like to review the final because then I
Okay.
haven't I don't want to record it. But I mean, we could meet and talk about it.
Right, we don't need to record it, just to have a review with the team if that is possible.
Sure. I have to see the schedule. The calendario.
Yeah.
The last day for me to submit the grades. Okay, so if I give you 3 days, 8 to 9, 9 to 10, 10 to 11, I guess we can meet on the 12. What is the 12? 12th is a Wednesday. Well, the grades have to be submitted on the 15th. I mean, we could meet on Saturday. We could meet on Saturday, just like regular. So the following week after the test, we can meet on the 15th. That'll be easier for everybody, I think. You agree? Than to try and fit it in during the week.
So the 15th is the last day that you have to submit the grades?
Yeah, so I will already grade everything, and then I'll just, after the class, unless anyone wants to dispute anything, you can. I'm just gonna submit them as is.
Right, so if we had any reviews, like last time that there was one that was a little bit confusing, would you be able to also, consider that for the final grade?
Yeah. Yeah, we can do that. Okay. I should have already done that though, because if I mark them already, then usually I look at that. Okay, so where were we? Horticulturalist wishes to estimate mean growth of seedlings in a large timber plot, a random sample of 100. So I put the equal sign everywhere here. So n equals 100, x bar is 5.62, and s is 2.5. So you have to read to make sure you do not have sigma. So verify you don't have sigma, because that is better than using s. In this case, sigma is unknown. So use the formulas of number 6.
Sorry, a quick question. So since we're taking the exam on the 8th, is due on the 11th, before the 15th, we will be able to see the grades on model, right? So before we
Yeah.
go to the review.
Yeah.
Okay, good. Thank you.
Okay. Can you try that? So you need T star for 95% and a degrees of freedom of 99. So what do you do? $99 is not here. Right? So which one is chosen in the, so let me take this portion of the table with us. Now you could get the exact value, remember, using Excel. Right? Let's actually do that before we go, and that's how we'll finish today. Okay, so here's the table. I'm going to put it on the same page so you can see. So for 99 degrees of freedom, 95% confidence, which one did they use? So you got to decide if you're going to use 1.984 or do you go down? So this is do you go to the closest one or go down? What did I say in the notes? If it's not there, if your degrees of freedom are not there. What did I say in the notes? Let's try the closest one. So it's going to be X bar, which is 5.62 plus or minus. The closest one is 1.984. S is given as 2.5. And square root of n is 10. So your margin of error is very small. It's 0.496. So check on the left and on the right. So I get 5.13. It looks like it's this one if I do that. Is that the right answer? So what I did was choose the closest one. It's really hard to read. Let me separate those. Let's check in Excel what Excel would give us. So in Excel, we want to find the right t value for 95% confidence. So 95% means 2.5 on each side, right? So we have to go equals t distribution inverse and put 2.5%, so 0.025 here, and degrees of freedom for us 99. And we get 1.984. Okay, so that is good. That's the best we can do. That's right, Marcos. Very good. Okay, so this is okay. It'll always give the negative because it always gives the left side. Okay, any questions? I'm going to let you go. You're going to have a good week, right? And then next week we will just continue. We'll do some of the review exercises, any questions you have. And that's it. Just keep studying and we can fill in the gaps if you understood this, but you didn't understand module 7 or module 6. We can go back and talk about that. We can talk about the quizzes if you have any problems with any of the quizzes online. So let's leave next week for just review. No new material, just we finished the material last week and I talked about everything I wanted to talk about. Let's just do some exercises. So try and complete most of this homework document. Any of the outstanding problems you don't know how to do, we can talk about. But you do have the complete solution set, although you might still not understand the solution. So bring those to next week's class. So have a good week. Thank you.
Thank you. Have a good weekend, everyone.
Bye, everybody.
Thank you.
Thank you. Bye.
Bye.